Okay, so welcome to our next session. So today we are going to have examples on simple strain, particularly on axial deformation. So when we say axial, we have already satisfied the conditions where the strain is constant. So we'll just have to apply the relationship between stress and strain in terms of modulus of elasticity. And as we all know, the formula is just simply equal to delta is equal to PL all over AE. So this is the basic formula that we need to apply here. So for problem number 1, we have a 20 millimeter diameter steel rod is hanged, suspended vertically from one end. It has a total length of 100 meters and it is carrying a light truck weighing 2,722 kilograms at the lower end, and then the density of the steel is given in terms of kilogram per cubic meter, as well as the modulus of elasticity, that is 200,000 megapascals. Okay, so as usual, we are going to draw the free body diagram. Okay, so draw the FBD. So we have here a suspended bar. Okay, and this suspended bar is having a weight and a force on the edge. So by this understood that there will be two deformation. Okay, the deformation on or caused by the weight, and the deformation caused by the force at the edge. So there will be a deformation on the due to weight, and a deformation due to the force or the weight of the truck on the edge. Okay, so this deformation is not necessarily located at the bottom, but essentially the distribution of the delta here due to the weight of the truck is occurring all over the entire leg. Okay, so we should note that. So it is occurring over the entire length. But for the sake of calculation, we'll just have to reflect it on the bottom. And for this one, this is delta due to the weight or the self-weight of the bar will just occur on the upper portion of the whole length of this bar. So if we have illustrate that this is delta due to weight and this is delta due to the force P. So let us have here now the P here. This is equal to 2,722. Of course, we need to multiply that by the acceleration due to gravity to make it on the force unit. So we'll be having a value of 26,702.82 newtons. Okay, and for the self weight, say this is the weight of the bar, that is equal to how much? Gamma times volume. So W is not directly given here. Actually, we need to acquire W. And for your information and advanced information, we have W is equal to gamma times volume. What is gamma all about? It is all about a value of the unit weight. The unit weight for your info is weight, the weight all over volume. So the unit here is weight, of course, first, and this is cubic meter, or if you want, Newton per millimeter cube. In English system, we have this to be pounds per cubic feet. Pounds per cubic feet. Okay, PCF. So what is the use of this one gamma? In every material, there will be values for gamma. Okay, there will be values for gamma. Why do we need to have values for gamma? Because we are calculating the self-weight of every structural element on structure. That is why the unit here is this one. Actually, we do not need to memorize this one, but to familiarize ourselves with the unit of force. And the unit of force is Newton, right? So if we have a force Newton per cubic meter, therefore, we'll just have to multiply it by cubic meter. Okay? So the resulting unit here is actually the weight. Weight is equal to Newton, right? Similarly, on English, if we have pounds per cubic feet, we'll just multiply it by the volume to come up with the unit pounds or weight, that is a weight. Okay? So in this case, we have here given density is equal to 7,859.5 kilogram per cubic meter. So this is density when we have a kilogram per cubic meter. Of course, if we multiply this by 9.81, okay, it becomes now gamma. Why? This is acceleration due to gravity. This is mass, right? Multiplying it by acceleration due to gravity becomes unit for force. So therefore, 7,859.5 times 9.81 becomes Newton. So this becomes Newton per cubic meter, which is gamma or unit weight. So by that, we'll have 77,101.7 Newton per cubic meter. So if we wanted to have the weight, of course, just go for the volume. Okay? So we can easily get the volume, right? So the volume is simply equal to the cross-sectional area times the length. So in this case, we have a circular area. So we should note that we have here a 20 millimeter diameter steel bar. Okay? And that is a circular cross-section. So we have here a cross-sectional area for circular section. We have pi over 4 times 20 squared multiplied by the total length of 100. So we'll be having a volume of okay. By the way, we cannot really have an inconsistent unit here, so let me revise that one. This is pi over 4. So if we are concerned by meter, then this should also be in meter, 0.02. This is cubic meter. Oh, sorry. This is squared and times 100. Okay? So we have 0.0314 cubic meter. So finally, W is equal to 77,101.7. So let me place the unit so that you can see that cubic meter here will just be cancelled. So we have an equivalent weight of 2,422.22 newtons. Okay, next we'll now go to the calculation of the deformation. So again, we have the total deformation to be equal to the sum of the delta due to weight and the deformation due to the track weight, so that the total stretch will be equal to stretch due to the weight plus stretch due to the force of the track or the weight of the track. So we need to apply the formula PL all over AE. Okay, due to weight plus PL all over AE due to the weight of the track, or P. Okay, substituting the values, the computed weight here, or the self weight of the bar, is 2,422.22. So we shall multiply it by the length. What is the length involved here? Perhaps you may consider the whole length. Again, it is not. When we talk on weight, only the upper fiber will be subjected to the deformation, because the concentration is again at the center. So the subject to stretch is, of course, this upper portion only. Okay, that is why the consideration in the length is that half of the length will just be considered. Okay, so that is equivalent to 50. This is 50 meters, so we need to multiply that by 1000 to come up with a millimeter unit. And I think we should already merge here the denominator. Okay, so we suggest now to merge our denominator into 1, because we have a uniform cross section, okay, and a homogeneous material, so there is no change in the area as well as the modulus of elasticity all over the length. So therefore, we'll just merge it into one. So we have here, the area was already computed here, equivalent to, sorry, volume. So let me write that again, pi over 4 times, this is 20 squared. So this is now in millimeters because all are set in Newton and millimeters. And E is 200,000 megapascals. And then we add the loading. And the loading is 26,702.82 times the length. This time we are going to consider now the whole or the entire length. So we multiply that again by 1000. So we come up with the total stretch. We have 44.43 millimeters. This will be the total stretch of the bar suspended from the ceiling. Okay, for the second problem, we have here an aluminum bar. Of course, again, this is homogeneous, only aluminum, there is no other material. And the cross section is 50 millimeter by 50 millimeter all throughout the length. So again, we have a homogeneous one. So compute the total change in length of the bar if our E is equal to 68 gigapascal. Assume the bar is suitably braced to prevent lateral buckling. As we observe here, that all of the loadings from the left are equal to the loadings on the right. So actually we have 8 plus 3 for the right, that is 11, and 6 plus 5 on the left, that is also 11. So it is good to note that we have a bar on state of equilibrium, so there will be no acceleration. However, it is a subject for stresses. So there will be different stresses on every sections of this bar. So as we can see, we have an indicated sections of the bar or the span of 2 meters and 2 meters to 5 meters, okay? 2 meters up to 5 meters and 5 meters up to 6.5 meters. So what we do is to have a cross section on every, or by section method. So we're going to have a section method on every section of the bar. Say we have here a section considering the left portion, another section considering the left portion also, and another portion. This time it is much convenient to consider the right portion. So let us label all the sections. Say this is section AE, this is section BB, and this is section CC. So this is bisection method. So considering section AE, let us illustrate what are the fibers involved on section AA. Only the left portion, of course. So considering the left portion, can be seen here that we have here 5 kilonewton. Say I'm going to label this as, or assume a direction, and label this as PA, and apply forces horizontal is equal to 0. We have PA is equal to 5, or shall write it properly, negative leftwards plus PA is equal to 0. So PA here will yield to a positive answer, 5 kilonewton. So when we have a positive answer, therefore our assumption for the direction of PA is correct, thus it will be maintained. So therefore the orientation of this 5 kilonewton is away from the joint. Therefore, let us simply indicate that we have a tensile orientation on that. Why do we need to indicate that one? Because having a tensile load corresponds a stretch or elongation, and then having a compressive type of force, we have a shortening of the bar, and that is indicated through a negative sign, okay, or a reduction or shortening of the leg. Okay, so next we proceed to the section BB. Moving on to section BB, considering the left portion. So first we have here a leftward 5. So on this section we have also have force of 6. Okay, so of course again it is obvious that this is going rightwards because it is just resisting a leftward direction. Okay, so applying now our equilibrium equation, we have summation forces vertical is equal to 0. Sorry, vertical, it should be horizontal, it should say. So therefore we have PB equal to 11 kilonewton. Now this should be in tension. Okay, so or shall we write it properly? Negative leftwards, positive rightwards is equal to 0. So just the same, we will yield a positive answer. And initially we have assumed to be rightwards or away from the joint, and found out we have a positive answer, therefore we maintain that direction to be a tensile orientation of force. Finally, at section CC, this is section BB, finally for section CC, we have to consider the right portion, and the right portion we have 8 kilonewton rightwards. So if this is 8, then it is assumed that this is PC against the direction of K. So perhaps you can directly say that this is PC is equal to 8 kilonewton. Again, that is in tensile orientation. So on our solution, there is no single force that is on a compressive orientation. So therefore, the delta of this one will just sum up, will just add. Okay, so delta total is equal to summation of delta. So the delta total is equal to delta A plus delta B plus delta C. We have PL for A plus PL for B and a PL for C. So note that all of the operations here is positive because again we do not have any compressive forces. So the denominator is merged into one. So let us see what is the area here. 50 by 50. So 50 by 50 times the modulus of elasticity to be equal to, we have 68 gigapascals times 68. And then we substitute the variables. So for PA we have 5 and a corresponding length of 2 meters. So we write that to be equal to 2000 plus, by the way, 5 here is to be multiplied by 1000 to make it in Newton, and then the length 2000 or 2 meters shall be written as 2000 millimeters plus 11,000 or 11 times 1000 times the length is 3000 plus 8 times 1000 multiplied by the length, which is 1500. Okay, all over 50 by 50 by, this should be 68,000. Okay, so finally we have the total elongation to be equal to 0.85 millimeters. So this is the total elongation for that bar. Okay, so please stand by for the next problem.